In March 2025, NASA released a James Webb Space Telescope result that forced Planetary scientists to take another serious look at Neptune. This wasn't the discovery of a new planet or some distant galaxy. It was a discovery much closer to home. Neptune. The eighth planet from the Sun, a world known to humanity since 1846. Webb had detected something in Neptune's upper atmosphere that researchers had spent decades trying to observe. For nearly 30 years, scientists had searched for evidence of a particular molecule associated with auroras on the giant planets. Again and again, the signal refused to appear. Then Webb detected it. And the clarity of the signal surprised the researchers themselves. That reaction is important because scientists normally don't describe an expected result as shocking. When something produces a signal far stronger or clearer than anticipated, it can reveal that our understanding of the system is incomplete. And Neptune has been doing exactly that for decades. The mystery goes much deeper than its atmosphere. Neptune sits roughly 4.5 billion kilometers from the Sun. At that enormous distance, sunlight is incredibly weak compared with what Earth receives. Yet Neptune possesses some of the fastest winds known anywhere in the solar system. So where does all that energy come from? The Sun cannot easily explain it. Neptune actually radiates significantly more energy than it receives from sunlight. Measurements indicate that the planet emits roughly 2.6 times the energy it absorbs from the Sun. That means Neptune has a substantial internal heat source. Somewhere beneath those clouds, the planet is still releasing energy left over from its formation and possibly from ongoing processes deep inside its interior. That internal energy helps power an atmosphere capable of producing enormous storms and winds reaching more than 2,000 kilometers per hour. Voyager 2 gave humanity its closest look at Neptune in 1989. But that encounter lasted only a short time. After the spacecraft moved away, scientists were left with countless questions and very few opportunities to answer them. For decades, Neptune remained one of the least explored major planets in the solar system. Then came James Webb. Webb's first widely released Neptune images in 2022 immediately showed why infrared astronomy could change the way we see this distant world. Instead of the familiar deep blue planet from visible light photographs, Neptune appeared dramatically darker in infrared. Its rings stood out with remarkable clarity, revealing faint structures that were difficult to see from Earth and even challenging for earlier space telescopes. The reason is simple but fascinating. Webb doesn't see Neptune the way human eyes do. It detects infrared radiation, allowing astronomers to study heat, molecules, clouds, and atmospheric chemistry that are difficult or impossible to identify in ordinary visible light images. But the real breakthrough came from spectroscopy. A spectrograph doesn't simply create a picture. It separates incoming light into wavelengths, allowing scientists to identify the chemical fingerprints hidden inside that light. In observations made in 2023, Webb's instruments examined Neptune's upper atmosphere and detected a signal associated with H3+, or trihydrogen cation. H3+ consists of 3 hydrogen atoms carrying a positive charge. This molecule is extremely useful to planetary scientists because it can reveal conditions in a planet's upper atmosphere and is closely connected with auroral processes. Scientists had expected H3+ to exist around Neptune. The planet has hydrogen. It has a powerful magnetic field. It interacts with the solar wind. The ingredients are there. Yet for decades, observations from Earth had struggled to detect the expected signature. Webb finally succeeded. And it didn't merely reveal evidence that auroras exist. It helped scientists map where those auroral emissions were occurring. That's where Neptune became even stranger. On Earth, auroras generally appear around the polar regions because charged particles follow magnetic field lines toward the magnetic poles. Jupiter and Saturn also have powerful polar auroras. Neptune doesn't follow that familiar pattern. Its magnetic field is tilted by roughly 47 degrees relative to its rotation axis. Even more unusually, the magnetic field is significantly offset from the planet's center. As a result, Neptune's magnetic poles don't sit neatly over its geographic poles. They are located much closer to mid-latitudes. So Neptune's auroras appear in regions where you wouldn't expect them if you assumed the planet behaved like Earth. Webb provided the clearest evidence yet of this unusual auroral geometry. The strange magnetic field may also tell us something about what is happening deep inside Neptune. Planetary magnetic fields are generally generated by a dynamo, where electrically conducting material moves inside a planet. Earth's dynamo operates in its liquid outer core. The giant planets have very different internal structures, with Jupiter and Saturn generating their fields through layers involving metallic hydrogen. Neptune is different. Its magnetic field doesn't resemble a simple, neatly aligned planetary field. One possibility is that the dynamo operates within a relatively shallow layer rather than deep inside the core. Such a configuration could naturally create a magnetic field that is tilted and displaced from the planet's center. Then there is the extraordinary chemistry predicted deep inside ice giants. Under the crushing pressures and extreme temperatures found inside Neptune and Uranus, carbon-rich materials may behave in ways completely unfamiliar on Earth's surface. Scientists have proposed that carbon could separate from hydrogen and form diamond structures deep inside these planets. Some models even suggest that those diamonds could sink through the interior, creating a bizarre form of planetary precipitation. It's often described as diamond rain. But the exact conditions inside Neptune remain uncertain. And that's the real problem. We have theories. We have models. We have observations. But we don't have enough direct measurements. That's why Neptune and Uranus have become increasingly important targets for future planetary exploration. A dedicated mission to the ice giants has been identified as a major priority in planetary science planning. A spacecraft could spend years traveling through the outer solar system before finally reaching Neptune, where it could investigate the atmosphere, magnetic field, interior structure, rings, moons, and the mysterious energy flowing through the planet. The difficulty is getting there. A mission to Neptune requires enormous travel time and careful orbital planning. Gravity assists, particularly from Jupiter, can significantly reduce the amount of fuel required and alter the spacecraft's trajectory. That means launch opportunities matter. A mission designed today could still take many years to arrive. Until then, telescopes like Webb remain our best tools for studying Neptune from afar. And every new observation seems to reveal another piece of the puzzle. There are also atmospheric temperature mysteries. Neptune's upper atmosphere has behaved differently from what researchers expected. Observations indicate temperatures that cannot be explained simply by the amount of solar energy reaching the planet. This is particularly interesting because Neptune receives only a tiny fraction of the sunlight Earth receives. Its atmosphere is therefore an unusual laboratory for studying how a planetary environment behaves when sunlight becomes extremely weak but internal energy remains important. If the models cannot fully reproduce Neptune's upper atmospheric conditions, that doesn't mean the laws of physics have failed. It means our models are incomplete. And that distinction matters. Neptune isn't just an isolated curiosity. Ice giant-sized planets appear to be extremely common around other stars. Worlds roughly between the size of Earth and Neptune occupy a major portion of the known exoplanet population. When astronomers study those distant planets, they rely on physical models developed from what we know about worlds in our own solar system. Neptune is therefore one of our most important natural laboratories. If we don't understand how its atmosphere works, our interpretations of similar planets around other stars could also contain uncertainties. The farther we look into the universe, the more valuable Neptune becomes. And then there's Triton. Neptune's largest moon is unlike almost anything else in the solar system. Triton is believed to have originated in the Kuiper belt and was later captured by Neptune's gravity. Its orbit is unusual, and its motion slowly carries it closer to Neptune. That process is driven by tidal interactions. Over an extremely long period of time, Triton's orbit will continue to shrink. Eventually, billions of years from now, Triton could cross Neptune's Roche limit. Beyond that boundary, Neptune's tidal forces would become strong enough to overcome the Moon's structural cohesion. Triton could be torn apart. Its fragments would spread around Neptune, potentially forming a spectacular new ring system.